Hi everyone, my name is Kaige. As you can see, today the project I was showing up is named Energy Flexibility for Water Utilities. And first, I want to show my respect to my supervisors, Professor Rebecca Young, Dr. Kazi, Professor Gary, and Professor Xun Yi. Also, the project partner on the left corner, Race for 2030, Civil Net, Colonial Water, Sydney Water, RMIT, and Monash. So, firstly, let's look at some of the background information of this project. So, in the past few decades, there are more and more PV panels and the wind farm have been installing in the power systems in Australia, also other areas in the worldwide. Although it reduces the green footprint, but it also causes several challenges, including the slower response in balancing the demand and supply in this power system, as well as a higher possibility of the frequency instability, as well as the increased occurrence of contingency event in the system. So, as a high energy user, with a lot of renewable sources and a low flexibility, water utilities, specifically referring to the water treatment plant, wastewater treatment plant, and water distribution system, plays a very important role in mitigating these challenges, while also they can, in the meantime, they can reduce their energy cost as well. There are several solutions by participating in different demand response programs in Australia and NAM, or make adjustment of their diurnal demand patterns, or leveraging the abundant renewable energy sources on their sites, as well as shifting the energy load to align with the renewable availability. So next, let's look at the project aim. So this project is also one of my main supported project of my PhD project. So it aims to develop an AI-powered tool to facilitate the decision-making on finding out the optimal load management and energy trading strategies that can support the renewable transition, as well as the energy efficiency of water utilities itself, while also benefiting to the electricity grid. So you can see this is the prototype of the tool. It's a software, but it's currently we are still on the phase of modeling the simulation and the reinforcement and training. And currently we are running on the MATLAB environment. So you can see if you input multiple of the parameters on site, such as the dissolved oxygen, optimal deoxygen, minimal deoxygen level, and also other parameters of the aerator sink, then you can find out the optimal operation based on different sites, the condition. So let's look at some of the method. So the core of this method is that we want to build up a AI machine learning agent model in the center, and through a series of intensive reinforcement learning training, so that we hopefully the agent can do optimal operation on different sites, for such as scheduling and shifting large load, and strategically charging or discharging the battery system at the appropriate timings. On the other hand, the agent can also facilitate the renewable energy trading with the neighborhood rooftop PV, and also participate in different demand-side management initiatives in the Australian national electricity market, also so-called Australian NAM. So, the algorithm we utilized is called the DTPG, Deterministic Policy Gradient Algorithm. So, as you can see, firstly, the agent observed in each episode. The agent observes the different price schemes or demand response signals from the different choices on the
vertical side, you can see the retailer contract, spot market, or the FCAS program, or the wholesale market, wholesale demand response program, and the RERT as well. And after the observation, the agent take different actions, including try different charging and discharging timing for the battery, or behave differently in engaging with the non-cooperative games with the peer to trade the energy, renewable energy, and also you can adjust the electric load at different hours of a day. Then the agent takes back of the rewards from the different perspectives, such as the economic metrics, including energy costs and the demand response revenue, and also it observes that it will keep the operational constraint. For example, the keep a safety margin in the treatment processes, etc. So finally, we will develop a agent that is capable to operate the system appropriately across various scenarios. So you can see the big metrics. We have so many scenarios. So yeah. Finally, we make it come true. The whole the pipeline. Currently, this is our Simulink and MATLAB model. Like you see, we have a water energy subsystem and a load management subsystem to simulate the energy dynamics on site, including water treatment plants and the wastewater treatment plants. And to link them together, we also developed an AI-based control system, as I introduced in the last slides. It's a reinforcement learning block. Yeah. So let's look at how the EIP platform race supports from here. Yeah, the font is a bit small, but yeah, initially I had a trial in my local machine. The major configuration is 12th generation of i9 Intel CPU chip. Unfortunately, my GPU is AMD. I was an AMD person until I wrote simulation. Yeah, just kidding. AMD is good. Yeah. Yeah. The time cost per episode, it takes 30 seconds per episode, and we estimate the overall episode will over 200,000 episodes to finish the reinforcement learning training, and in total it will take 23 days to complete the reinforcement training. So that's why I chose the AWS Cloud Computing server with a T4 GPU attached in the server. So the time per episode is narrowed down to 10 seconds, and because I separate the scenarios into 5 groups, and each and I deployed one agent at each server to run the reinforcement learning training under several scenarios. So yeah, each agent will take to 40,000 episodes. The estimated time cost will be 2.5 days each agent, because thanks to the parallel training capability, the overall time will be the longest time of each server, which is 2.5 days. So I realized the 9 times speed up of the training speed. Yes, of course, theoretically, I can split more scenarios because I have a so big metrics. I can split further, so that theoretically I can speed up the training process by 36 times. But I think that's not that is actually not necessary, because 2.5 days is actually reasonable for our research project. And finally, this is one of the trial from this the training. You can see the episode rewards training up very well, and it's the estimated rewards will converge at some time when we finish the training. So so thanks, Ray. It significantly reduced our research timeline. So saved over conservatively 3 months at least for the training work. It also gives me more opportunities to try different algorithms and also fine tuning the algorithm as well. So yeah, so let's look at the impact of the project. So in the case study of one of the wastewater treatment sites, Coleman Water, the AI-powered decision-making model demonstrated the potential to reduce their total cost by 40%, translating to millions of dollars per year. And the initial investment will be about $6 million per $6 million, and the payback year will be 4 to 5 years, which is fairly short, I think. And in the next step, we'll find out the best best algorithm and train the most confident agent, and then we will wrap up everything into a decision-making software. And this tool can potentially guide other water utilities and high-demand energy users to improve their energy flexibility as well. And on the other hand, it also can support the power system in accelerating the process towards the net zero emission targets in the future. So, yeah, thank you. That's all.